Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
All right, let's take a look at our homework for part 2 of lesson 4.3.1. Problem number 80 starts us off with Daisy and Alexandra each have a group of algebra tiles on their desks, as described below. So Daisy, she has an x, an x squared, a 1, another x squared. So they're not in any particular order, right? So I'm looking at that and I'm thinking, all right, how many x's are there? 4x tiles. Those are the skinny rectangles. How many x squareds are there? 1, 2, 3. So those are the medium-sized blue squares. And then how many unit tiles are there? It looks like there's one of them there. Okay, and then let's look at Alejandra. And how many x's does she have? She's got 1, 2, 3 of them. She's got 1, 2x squareds. And how many single unit tiles? 1, 2, 3, 4 of them. So to sketch them, let's start with Daisy. Here are her 3x squareds, right? 1, 2, 3 for 1, 2, 3. Here are her 1, 2, 3, 4 x's, 1, 2, 3, 4. And then she's got the 1 unit tile right there. And then Alejandra, she's got how many x squareds? 1, 2. She's got 3 x's, 1, 2, 3. And she's got 4 unit tiles, 1, 2, 3, 4. So if they put them all together, this is the idea of combining like terms. This particular expression we would say is, let me do this in blue, we would say this is 3x squared plus 4x's plus 1. And then to that, we're going to add 2x squareds plus 3x's plus 4. So how many do they have all together? Well, when we're adding numbers, we have to line up decimals, right? We have to go from left to right in case you need to carry over. But when you're adding algebraic expressions together, it doesn't matter what order you go in. I'll still start at the right and say we got a total of 5 1s, a total of 7 x's, and a total of 5 x squareds. So that would be the solution after you put all of them together. Copy and complete the portions web at the right. Okay, so with portions, we're talking about fractions and decimals and percents. So we know it's 21%, so we can write that as a fraction because it literally means 21 out of 100. And then we'd want to simplify that fraction, but it's already in simplest form. So there's no simplifying that. And the decimal equivalent is already there, 21 hundredths, 21%. Now the only thing left to do is just write the words. So do you want to write 21 hundredths in decimal form or in fraction form? And they're the same thing. So you can do that. I doubt anyone wanted to draw a big square with 100 individual squares and shade in 21 of them. So probably the words are easier to do than the pictures. All right, this is an interesting conversation to have. It has really nothing to do with anything we're doing in chapter 4. But still, it's good to talk about geometry every now and again and practice it so that when we get to chapter 9 and we're going to start working through problems that involve geometry, we'll know what we're talking about. So for each of the shapes below, choose one of the names on the list above them, best describe them, okay? The word best is important because some of these, like a parallelogram, there's lots of different types of parallelograms, right? A rectangle is a parallelogram, so is a trapezoid. We want the best name, okay? So I've listed in these situations every name, and then I will highlight which one is the best name. So be as specific as you can. So, all right, a right triangle. Triangles can be described based on their angles and based on their side lengths. So a right triangle has one right angle, obviously, that's why it's a right triangle, but it could also be scalene because it's got 3 sides that are different length. So the different kinds of triangles, you got your scalene triangle, you've got your equilateral triangle, means that all 3 sides are exactly the same length. And then there is a third type that's called the isosceles triangle, where 2 of them would be the same, but that's not one of our options here, and that is an isosceles anyway, so we don't have to worry about that. So the best way to call this technically is calling it a right scalene triangle. So you know 3 sides are different length and it has 1 right angle. This is also scalene, although those two look like they're relatively close, but they're not. And there's no option for an isosceles triangle up here anyway. So it's definitely scalene. And it's not right because there's no box, right? That's not a right angle here. A little bit wider. So if this is the angle that's a little bit wider than the right angle, then this would be an obtuse angle, which makes this an obtuse triangle. So, oops, stop it. This would be considered an obtuse scalene triangle. Now for this one. This can be considered a quadrilateral because it's got four sides, right? But that is the least specific name for any four-sided polygon. The next most specific name would be a trapezoid. And with a trapezoid, you've got two sides that are parallel to each other. And I should say at least two sides that are parallel. So the next classification would be a parallelogram, and it's not a parallelogram because these two sides are not parallel to each other. So we have to stop at trapezoid. So you could have called this a polygon, you could have called this a quadrilateral, or you could have called it a trapezoid. And trapezoid is the most specific name that you can give to this particular shape. Which brings us to this guy. It's a polygon because it's a closed figure with side lengths that are line segments. It's quadrilateral because it's got four sides. It's a yes. It's a parallelogram. No, hold on for a second. Actually, it's a trapezoid because it's got at least two sides that are parallel. It's a parallelogram because it actually has opposite sides are parallel to each other. So that defines it as a parallelogram. So the parallelogram is a more specific name than the trapezoid. But the most specific name for this would be rhombus because it's got four sides that are equal in length. Now, if you decided the best name for this was parallelogram because you didn't think all four of those sides look like they're the same length, then I would accept parallelogram. But with me looking at that, thinking all four sides are the same length, I'm going to give it its most specific name, which is a rhombus. Now, if this rhombus had four right angles, it would still be a rhombus, but then we would call it a square. Does that make sense? If it were a parallelogram and not a rhombus, and it had four right angles, then we would call it a rectangle. So a rectangle is a more specific name than a parallelogram, and a square is a more specific name than a rhombus. But technically, this can go by a lot of different names. It's a polygon, it's quadrilateral, it's a trapezoid, it's a parallelogram, and it's also a rhombus, and I believe the rhombus is the most specific name. All right, and then our diamond problems. Copy and complete these diamond problems. Remember, you multiply these two numbers together first, and their product gets written at the top. And when you add those two numbers together, their sum goes on the bottom. So here you go. -8 times -6 is -48, and -8 plus -6 is -14. Now, when you get into these problems, you have to use some algebraic reasoning. What number do you multiply times 12 to give you -96 for an answer? Well, when you divide -96 by 12, that will give you the answer of -8. We know a -8 goes there. So now we can add those together and get +4 for an answer because a positive plus a negative means you're going to do a subtraction. 12 minus 8 is 4. And you'll keep the sign of the number that had the greater absolute value. So you had more positives than negatives. So after canceling out the zero pairs, you're left with 4 positives there. Here we would do the same thing, but we would do it with adding. If you take 0.3 plus x, you're going to get 0.5, which means x has to be 0.2. Now, when we multiply them together, you're multiplying two numbers that are decimal numbers, so you're going to multiply the number and keep track of the decimal places, and that goes back into your answer. And then for our last one, this is the trickiest of them all. This is the one where you have to ask the question, what two numbers can you multiply together to give you -20 that when added gives you -1? So I'm going to go through, and since my sum is a -1, that means that the bigger of the two numbers has to be the negative, right? So you got to have more negatives than positives. So it's either going to be 1 and -20, 2 and -10, 4 and -5, and that's it for our options because there are no other combinations that would give you 20 for an answer. with the bigger number being the negative. So when you add those together, you get negative 19. These you get negative 8. This you get negative 1, which means this is the combination we're going for. The 4, sorry about that 4 there, it's a little floppy. The 4 and the negative 5. All right, Daniel needed to paint his patio, so he made a scale drawing of it. Here's his drawing. It's on a 4x7-inch card. He knows the width of the patio is 10 feet, but the scale drawing is in inches. So we need to figure this out in feet. And a lot of students think, hey, I got to do some conversions here because we can't do inches and feet. But you know what? There's something really interesting that happens here. When you're using proportional reasoning for these scale drawings and the actual dimensions, the unit of measurement doesn't make any difference. You just have to find the corresponding sides they put together. So this is the height for each one for the patio and the drawing, and this is the width or base for the patio and the drawing. So we're just going to set up these ratios, and you can actually set them up a few different ways. If I want to put the patio over the drawing and then have this be for the height, and this one could be for the width. So you'd want to have the X and the 10 going in the same region, so they will be in the numerators, and the 7 and the 4 go in the denominators. That's one way to do it. Or you could have said, all right, what if I take my 10 and my 4, so this will be for the patio, and that will be for the drawing, and so we're going to put the X because that's in the patio, and the 7, that's in the drawing. It technically doesn't matter because look what happens here when we do our cross multiplying. We're still going to get 4x's is equal to 70. We're still going to get 4x's is equal to 70, right? So in this case, you might have chosen to use a giant 1 and you think, what do I multiply times 4 to give me 7? I'll multiply 10 times the same thing. Okay, that would work. Or here you're saying, what would you multiply times 4 to give you 10? Multiply 7 times that same number, that will give you the same answer. But when we start getting into less friendly numbers like this, I want you to just do the cross multiplying. So what is 70 divided by 4? 70 divided by 4, let's use our calculator. 70, stop it, 70, stop it, try again. 70, there we go, divided by 4 is 17 and a half. Okay, so that has to be length of the patio, and it doesn't matter, it's feet, right? This one we were talking inches, this one we were talking feet, so it's going to be 17 and a half feet. Now, find the area of the patio. Well, the area is equal to base times height. So 17.5 times 10, we're just going to move that decimal one place to the right. It's 175 square feet. Now, one can of paint covers 125 square feet. So that means that 2 of them would cover 250 square feet, right? And 4 of them would cover 500 square feet. Well, we only need enough to cover 175 square feet. So 1 can won't do it, but 2 cans will. So we'll buy 2 cans and then we'll have some leftover spray paint in the can. And that ends our homework for 4.3.1. So, all right, let's move on to the next activity. Take care. Oh no! What did I do? Is it still recording? Oh, good. That could have been a disaster. Bye.